including something about texture. And so I am ready. When you said, okay, I can start.
Okay, it looks like we have a number of people who joined and they're not connected to audio, so why don't we wait just another minute or two?
Yes, sure, absolutely. But you said that could be my problem? I need to do something more from my computer?
No, you're good. You're good.
Okay.
Yep.
Great, thank you.
You want to just wait, that'll be fine.
Sure.
I have my webinar. It looks like some people are having slow connections to the audio.
Okay. Great.
So just give it another minute here. And where are you located right now?
Stockholm, in Sweden.
Okay, so what time is it for you?
6 o'clock in the afternoon.
Oh, okay, not too bad then.
No. It's okay. It's only dark, very dark here.
Oh, okay. We have the next presentation will be by somebody in Australia, and
Wow.
and they asked if we could change the time because otherwise it was like at 2 a.m. or 3 a.m. for them. So
Yeah. I was afraid of that, but I think that it was okay. For me, 6 o'clock is perfect.
okay. All right. Well, why don't I get started introducing you, Fernando, and letting everybody know what's going on here, and then from there you can give your presentation. So thank you for joining us for the 12th seminar in the Plant Phenome Journal monthly webinar series. My name is Seth Murray. I'm an editor with the Plant Phenome Journal, and I was the one who handled Dr. Mendoza's article. So I will be moderating this discussion. And Dr. Mendoza is a researcher now in Sweden. When he originally did this work, he was at Michigan State University in the Department of Plant, Soil, and Microbial Sciences as an associate researcher. He did some very innovative work in this paper, I believe, for using hyperspectral imaging to look at cooking time in dry beans. Once Dr. Mendoza finishes his presentation, we will open it up for questions. You can type questions, or if you have any issues, in the chat box. I will try and monitor that. You can tag it to everybody or to either the speaker or myself. And we will also unmute you, and you can unmute yourself and you can ask questions at that time. So I guess without any further ado, Dr. Mendoza, please, looking forward to your webinar.
Thank you so much for this opportunity. I appreciate. Thank you so much, Professor Seth. Really, for me, it's an honor to be here and also to have this opportunity to present my work when I was there in working for USDA and also for Michigan State University. This I try to add some information in addition that the information that appears in the paper, because we have around 5 years working in this area, trying to improve the models and to try to know if these techniques are able to predict as we expect. The title changed a little bit as the article appears, but here the title is Prediction of Texture and Cooking Time in Dry Beans using visible and near-infrared spectroscopy and hyperspectral imaging data. So, because we are working with beans and dry beans, we are trying to predict two important quality parameters that are texture and cooking time. Of course, we need to talk also about a serious problem, a problem that is very well known, that is the hard to cook. That is a problem that we know that is take longer to tender the beans. And this is one thing that we are trying also to take care here and to consider at the moment that we are trying to predict these quality parameters. So let me to start here. I want to present the outline of my presentation. First, I am going to present the aims of this project that I was working with the people there in MSU, also with some background. Then I am going to present in a simple way the optical methods for predicted end-use quality of dry beans. I am going to explain the terminology of that, why is this end-use quality. Later, we are going to present first the texture, but was one of the things that we worked before to go with cooking time, and this is the texture to measure the firmness and softness of the beans by using, in this case, NIRS spectroscopy and also hyperspectral imaging. Another thing that is very important is the water uptake, the amount of water that the bean is able to take. This is also, we try to predict that using hyperspectral imaging. The another was cooking time, that is the subject of the paper, and we apply that in soaked and unsoaked beans. So later we are going to present some model updating. This is only one idea that we start at the end of the paper. We present this at the end of our paper, and we are going to show some cross-year validation using these models, and finally some conclusions that probably we are going to, with some questions that if you have any question, please, I am open for that. So after that, one thing that I want to also to say thank you to all the people that I work in the past there in the plant soil and microbial science department. A couple of things that I want to say that for me was great to work there, because to face this problem in bean quality, we was conforming a multidisciplinary team that involved plant breeders, of course, the main people was there, biologists, food technologists, and also nutritionists that are all very important to be able to get these results that I really, all the people there helped me a lot to be able to get all this information, and also to interpret and to know where we can improve the modeling of that. The goal, as I mentioned, was improve the phenotyping quality traits of dry beans, and we manage all the technological and nutritional properties. We collect a huge amount of bean genotypes that was made for my partners, for all the people that you can see there that are seated around the table, and also the person that was responsible and helped us to lead the group was Karen Sishi from USDA, and also Dr. Kelly, James Kelly, that was represented to Michigan State University. It was a great group, and thank you. I want to introduce them because really, until now, I miss them, of course. But let me go to the next slide. This is the overall goal of the project that at this time was set for my research. It was to implement a visible near-infrared spectroscopy and hyperspectral imaging techniques for the automatic, non-destructive, fast, and economical end-use quality prediction of external and internal properties of cooked dry beans. We tried all, of course, because we were trying first, if we start to measuring, for example, the color and appearance scores, as we can get from a sensory panel test, and then with the information that we get with these instruments to try to predict that. Another was the water uptake after soaking of seeds. That was also very important. Is another parameter that we need to take care, and we are going to present here in this opportunity some results. The texture, that is the firmness and softness of the beans, and finally, as I mentioned, the cooking time. So, but one thing that I want to start is to explain something that probably many of you that are now in this presentation know very well. But I think that it's important to make the difference and to start to explain. I like this slide because really explain what we are trying to do. We use light, so we need to know first that when the light hit the surface of the bean, the first thing that we are going to have is some reflection. If these reflections is normally we know as the brightness of the bean, and also gloss. That is a very important quality in food science, and also when you are trying to measure the quality of foods. The another one that also is the concern of this presentation is the scattering, but this is when the light goes some millimeters inside of the seed in this case, and also some light that is going to transmit through the complete bean, and you can also detect that and collect this information. Finally is the absorption, that is the light that is going to be inside of the bean. Sometimes we can measure that with some by difference of that. So scattering is a physical phenomenon. This is what we are trying to measure here, because we are trying to measure the texture and also the cooking time that is related to the microstructure or the structure of the product. The another is absorption, related to chemical composition, and is another way to do that, but is that many people in chemistry use to solve many problems. But here, we are, one big difference is we are starting from the dry seeds. We are not going to prepare any sample here. So in this next slide, let me to explain a little bit exactly what we are going to try to do. The goal is predict the end-use quality from intact dry seeds using this optical sensor that I mentioned. So you can see these small dry seeds. We are going to use the sensor for that, but we need to take care that we are going to face some really complex problems. First is all the physical, chemical, and microstructural change that they are going to happen when you cook, or you have this product, for example, when you can the beans. And then we are trying from this initial information from the dry seeds to try to go and to evaluate the end-use quality of this product. But if we are going to have these signals, of course, we are going to try also to extract information of various phenotypic properties, but at the same time. That's the main idea, and this is what we are trying to do. From the dry seeds to try to predict after cooking, after the beans are cooked. So in my next slide, also here, I want to mention that this is the additional factors that we have, for example, is related to the genotype diversity, phenotype diversity, growing environment, post-harvest and storage condition that also are important. Of course, the cooking method. All these variables are going to affect that. It's not a simple system, and to be honest, when Karen Sishi offered me this possibility to do something, I was not convinced that it's going to work. But after work with many samples, I think that we found very interesting results. That this is the purpose of that I am trying to show you. But this is, well, there are something that is important to understand first, and I am trying to give some insight about that. Probably you have some knowledge about that, but let me to show what happened in the cooking process of dry beans. We have two steps. That is the normal way that we cook the beans. That is, first is the soaking, that we are going to put the beans in a container with water, probably with some salts, and we are going to try to take this for some hours. The first thing that is going to happen here is that the seed coat provides a physical barrier to the cotyledons. That the idea is the water need to arrive to this place. But in this first stage, water penetration occurs via the microfilm or helium, or also through the seed coat itself. But the concentration of water at this stage at the other coat is increased, but it's going to increase exponentially. Eventually, some water is going to arrive to the cotyledon, but this is not going to be the main purpose. More is going to swell the seed until saturation. Then, when the cooking starts, all this imbibed water reach the cotyledons. That this is the idea, and we are going to start with the partial solubilization of the cell walls, gelatinization of intracellular starch, and denaturation of proteins. Also, the pectin substance decomposes, and the connection between the cotyledon cells weakens, and the shedding strength decrease. That is the objective. At the end, we are going to get a soft beans cooked in a reasonable period of time. That is what we are looking. But this is in a normal condition, and this is what we expect. And the main reason of the soaking is to make easy the cooking of the seeds. So in the next slide, we need to face another problem. That is when the beans are not stored in the best conditions. We know very well that the high temperature and humidity are susceptible to the hard-to-cook phenomena. This makes long cooking time periods. So happen here all the inverse, because we start the breakdown of phytic acid. This is going to make some free divalent cations, is calcium and magnesium, and make this a structure that is very rigid. Also, the polyphenols become less extractable and interact with the cell wall, reduce solubility of cell wall pectin, and cell separation and starch deletalization is reduced. So, reduced protein denaturation also. And you can see a figure that was a very nice figure that we can see the microstructure of the products. But there are another one that also caught my attention, and it is that. This is because also we are going to see some major structural difference when we are talking after cooking, when we can see, for example, the soft bean and hard bean. In this case, in soft beans, the middle lamella between cells is, can you see, almost dissolved during cooking. Does not happen in the case of hard bean, because it remains and binds the cells together, and it's a very rigid structure, as you can see. But this is the reason when we bite the beans, for example, for soft beans, happen that is going to be some sliding of the individual cells. In the another case, if we bite the hard beans, we need to fracture the cellular material. This is a very nice way to describe what happened and what is the problem that we need to face in this kind of problems. But let me to return to our subject. This is only to know and to show what is the problem that we need to face in all of this evaluation. And this is the techniques that we have implemented in our lab in MSU. If, for example, this is the visible near-infrared spectroscopy, that is a technique very well known for many people. If we use, at this time, the reflectance mode, we use in the range of 400 to 2500 nanometers. In general, people use that for chemical, to identify and to measure chemical properties. We extract from there around 1050 wavelets that we use to model. You can see there the graphic. This is for a set of beans that looks very close, but there are different that we can identify there. This is after the signals were normalized. Then we pre-process this information, these signals, to extract the best wavelengths and then modeling, and to try to predict all the quality parameters from intact dry seeds. But there are one thing that is important to consider, that visible near-infrared spectroscopy is very good, but the problem is not provide the spatial information. And this is critical when you are trying to test, at least for food inspection, because the variability in food is very high. But this is one thing that we need to consider also, probably with some measurements, with additional measurement to the same set of samples, probably we can get good results. This is one thing that we are going to see later here. In the another case, we have a hyperspectral imaging. This system was set up in the labs of USDA, where I was working there, and we use a Petri dish where we organize these dry seeds, and there, in fact, hyperspectral imaging is the combination when we have imaging data with a spectroscope. That means that we are going to have a spatial and spectral information to get a very huge amount of data that we know very well as hypercube. And then we are going to be able to evaluate, for example, internal and external properties, and also defects, because we are going to get an image from that, and also chemical properties. This is the hypercube. That means that we are going to have, in this case, we work for 400 to 1000 nanometers less, because these systems, you know, that are very expensive, is highly dependent of how many wavelets you have for that. We generate here 500 spectral images, but images in the visible range and also in the near infrared range, because this is almost close to 1000 nanometers. So with this information, these images are very rich. It's a lot of information, But something that is important to do is to work with the image processing of that. We need to have some expertise to process that. The idea that we get, because all these images have the seeds for the same, for the different wavelengths, we have that exactly in the same position. So you can see, for example, the image, the gray image at 725 nanometers, we can try to linearize that and to get a mask. With this mask, to try to extract only the true information from the beams. I mean, the silhouette of the beams. With this information, we get the average for each of these images, and then we get this kind of spectra that you can see here that is more simple because they are running for 400 nanometers to 1000 nanometers. We make the same, we apply the same because now we have signals, we preprocess that, and we make the model to make some quality prediction, again, from the intertract seeds. So after that, another important step on all of this is the preprocessing for the automatic prediction. Here, I want to present, for example, we have a step that is the spectra that we are going to get from the NIRS spectroscopy, as I showed before, and also the hyperspectral information. Then this data need to be preprocessed, then a feature selection, and then a prediction process. So to do that, for the preprocessing, the first thing that we need to do is the normalization of the data. Because, of course, we need to try to set up, or in particular, to normalize the amount of light, because it's highly dependent. Not all the seeds have the same size, if this is a problem. So then we probably sometimes to apply some preprocessing methods that are very well known. For example, when you smooth the signal, also the first derivative, second derivative, another one was the continuous wavelength transform. But one thing, after trying so many times, we found that, for example, using the two-band ratio, that means that using for each of these preprocessing techniques, we get the two-band ratios. The combination, for example, after applying continuous wavelength transfer, using the two-band ratio, we got the best results. So then, because we generate a lot of information only from one type of sample, we need also to select what is the best wavelength for that. We use a simple method that was the sequential forward selection method. We select only the best 100 features. From this data, this is critical because here we use partial least square regression model to try to get the numbers and to know if we are able to predict or know this system. One thing that I want to mention here is that there are many ways to process that, and also today there are very powerful methods. And let me to say that 1 month ago I was in a fair in machine vision in Germany and was very surprised because people that is working with deep machine learning really make a very good results. Here, what we are trying is to show that our hardware is able to predict something. This is open, and probably many people is able, with more expertise on that, to apply another platforms or another methods that are going to improve the results that we are going to show here. So, but there are another important thing that I want to mention here before to go to the results. When we make this model, we know that we need to make some calibration models, I mean to build our models, and for that, from the samples that we got from each set of samples, 75% were made for calibration, and the rest 25% for prediction. We ran that 4 times in the way that at least each sample that was in the prediction was also in the calibration test at least 1 time. So in this way, we got the average number of factors that we need to build the model, the R values for calibration, the standard error of calibration that we get. But the most important was that from the 25%, that is like let me to set an independent set. That was the average of these 4 runs, and we get also the standard error of prediction. The results that we are going to show here are related to this independent set. I mean the R prediction and the standard error of prediction. We are focused more on that because really the other ones are good, but we are trying to show what is if the model really is able to predict or not. So with that, and taking consideration that, let me to go to the texture prediction in canned black beans. This is the standard method that we have in our lab there in the barn that we work with the beans. This was make texture prediction for canned black beans. Here we take 100 grams of canned beans and we use this standard shear compression cell that is very long method, works well, the results are very consistent, but the problem is take longer and we need to take care of, to get, we spend a long time doing that. So the idea here, let me to show first the canning process that we have there in our lab, because I think probably know many of you are related with that. But first, we have the seeds and we try to remove all that are not good. The soaking process that I mentioned is very important. The filling of cans using the same weight to put in each of these cans. Then the addition of the brine solution to know to exactly put how much brine we are going to put in each of these cans. We seal this and the sterilization process and the cooling. We keep that for 1 month for some stabilization before to open the cans. So this is the experimental design for predicting the texture of the beans. So in this, let me to show and to describe how or that. The first, we start with the black beans. We work with black beans from different sources. They were harvested in 3 different seasons, from 2013 to 2015. We start with the dry beans. We soak this bean, as I mentioned before, for 12 hours, and then we made the canning process. Then after 1 month, these were opened and then drained. But we get the information just from the instant dry seeds, dry beans, using NIRS spectroscopy and also hyperspectral imaging. And at the end, we measure also the texture measurement with the compression test that I showed you before. If we try to correlate this information and to explain this texture measurement using the information from this NIRS and hyperspectral imaging. So this is the results that we got from our test. I want to show here that we use different sets of samples, as I explained, coming from different years, some of them in mixing from 2013 and 2014. That's very interesting because the first set, or set 1, was 190 samples, but this only was 3 varieties. It was very homogeneous varieties. It was very interesting because this only has a coefficient of variability of 9.6. The another was the set 2, that was 92 varieties from the major US bean breeding programs that come from many places and was coming only from 2014. And the coefficient of variability was very high. The set 3 that used 63, this was only for 2015. But also to know, this was intentionally considered that, because we know that the distribution and the variability can affect the robustness of the model. So at the end, we put all together the 3 sets of samples to be able to know what happened and what is the results when we try to predict with this information using all the data together. Let me to show what is this is the distribution. You can see that not all the distribution are as expected. Not all of them is, the ideal situation is that you have like to a Gaussian distribution to get something that you can repeat. That's what we are trying to test. You can see here that they all have different distribution, and only to measure something people that at least the information said that the good beans to taste is from when they go from 55 to 65 of texture. No, this is has been considered as a good quality. But this is the sample that we have. This is what we are going to try to predict. So in the next slide, we are trying to present here what we got with this NIRS spectroscopy. Can you see the three varieties? This is the first column, show the average factors, no? That also the next one is the R prediction, and the next one is the standard error prediction. So call the attention that the first, that was the most homogeneous, only three varieties, in fact was a very good set of samples. We got the best results, followed for the 92 varieties, and then for the 63. All of them, when we put all together, we can see here that we have a total of 20 factors, and this is the result that we got. But it's also interesting to compare the result with hyperspectral imaging. And you can see that probably the factors were almost the same. We need to consider also here that the result or the wavelengths or the range of wavelengths was not the same for both technologies. This NIR used from 400 to 2500, and hyperspectral imaging in this case used from 400 to 1000. There are important differences, but we have in hyperspectral imaging is more resolutions. We have the spatial resolution of that. So we can see that the results were pretty decent, but let me to say that better was with this NIR spectroscopy. So that's interesting because I would like to show you what we got when we put together the three samples. And this is the same, but sometimes the figures show better the results. In the x-axis appears the actual texture as was measured with the instrument. And another one is when we use the model. One is the calibration, that we use the 75% of that, and the another is the prediction. When we can see that the correlation and almost they predict pretty decent the results. This was for this NIR spectroscopy. If another one was for hyperspectral imaging, that you can see also that the results are pretty decent, probably a little bit more of variability, but was expected, and probably we have more data. If we increase the number of wavelengths, I feel that the results could be better. That's what my thinking first. This was published before, and I think that was a good contribution. But now we went to another set of samples. That what I want to show now is the advances that until the time that I was there in cooking time prediction. To start with that, I want to present you the method that we have. This is the standard method that we have implemented in our lab there. And this is what we use. All the people is in charge to get information from that. I think, let me to say, they are expert doing that, because you need to take 25 beam seeds. It's a very hard work, very, very hard work, probably worse than take information using the texturometer. The idea here is to get information from these 25. If we use this pin drop with these needles that is going to, you need to put all the system inside of the boiling water, as you can see in the right picture. And what we measure there is when the 80% of the samples or the needles pierce the full beam. This is what we have defined at the cooking time. So after that, let me to show what was our experimental design. We use exactly the same. We use here, in this case, an Indian diversity panel that was collected from 2014 and 2015. We start with the dry beam seeds. We scan these samples. We use at this stage hyperspectral images for 400 to 1000 nanometers. Unfortunately, we were not able to get all the information for this NIR spectroscopy. It was a little bit hard to follow all together, so many samples, but we got that from hyperspectral images. And we test two sites, unsoaked beams and another one, the soaked beams, because we would like to know first what is the difference, what could be easier or what could have better results. Then, in both cases, in the soaked beams, you can see that we measure using the standard method to measure cooking, the same that we make here. The next step was, from the scanning, was in the soaked beams to try to predict the water uptake percentage. Only by difference of the weight that we get that, and also from the same information to try to predict the cooking time. After that, let me to show some examples of the Indian diversity panel that we work here, coming from different places. Was very interesting to have all of these in our lab. The samples including 5 classes. That was, I think, that is the most commercial ones that we have, as I know, and probably my colleagues in Michigan State can give more information about that. And we scan raw before any processing, so even before soaking. So this is the sample that we got, and then let me to show now the results that we got for that for water uptake using the partial least square regression model. As I mentioned, this was collected only by difference of weight, and we saw this sample for 12 hours. This is always I like to present you the histograms, because it's a good way to know what is the quality of your data. We can see there that we have a Gaussian distribution, Gaussian distribution, with a pretty decent wider information that we are trying to model. So this is the results, again, using the different preprocessing methods. You can see that the continuous wavelength transfer at this stage, using the 2 band ratios, again, was the best, as you can see here. And then this is the result that we got. That was probably not the best, but they were pretty decent to the result that we are looking. And because not, that means that when when I am trying to say that was not probably too much information. We had here only 135 samples, and probably we need more representative number of samples for that. But this is what we use for this test. The next one was the histogram for cooking time, but this was for soak and unsoaked beans, that was we are trying to measure. Here we use a set of 14 edible dry beans. They're coming from 2014, and you can see the difference for soak and unsoaked beans. It's interesting to see the difference between the cooking time, the range of cooking times. And also we can see in the histogram that we present here. One interesting thing that called the attention of my colleagues in genetics was that here overlap some of these cooking time. In particular, you can see, for example, from 85 until 165, there are some samples that probably don't need to be soaked. This is one thing that probably they are following now. But consider that this distribution is complex. So at the moment to make our models, we use only some set. For soaked beans, we use the part that was more representative to get a Gaussian shape, and this was around 85. And another one was the same, that ran for 85 to 135. So the results for the cooking time prediction by hyperspectral imaging, we gain, again, we use the partial least square regression model. It was for unsoaked, we can see again that using the 2 band ratios give the best results. But the cooking time, the error was 10.2 minutes. For the soak, of course, we expect that it was more homogeneous, but also the R value were better, and the standard error prediction was 7.7. So doing that and using this information, let me please to show in a figure what happened here. As I mentioned, in the x-axis, we have the actual cooking time that was measured by the standard. In the y-axis, we have the prediction model, how this predicts. The results show a very good prediction. I feel that this need to be improved probably with more data. It was the moment when I submit this paper, but a good idea, and don't expect, probably was the editor asked me, no, you need to confirm, even when you use the 25% of this sample to use for modeling that is working well, you need to retest that with a new independent set of data. So one idea of that was we got some information later from 2015 that was there We scan that, but never I process that. So I decide to use that. If this is, that's only for soap beans, because we have for soap beans. But what the strategy need to be different here. What we use here is, for example, we start with the number of samples for 2014 with 120. If we use only the 120, and then we predict the 80 samples that we have for 2015. And you can see that the results, at least the average for the standard error prediction, was terrible. Then we remove 5 samples if we start to play in this way. Probably you can say 5 or 10 could be not too much different, but makes a difference because the values start to decrease immediately. Even when we get, for example, 90 samples, if we use only 30 from 2015, and we use the rest, or 80 samples for the prediction, we got a values of 3.6. We decide only to take this, to know that, to recommend that we are going to use 100 samples, for example, for our calibration model. We use 20 for the new set, and at the end, we test with the rest, with 80, if we get these values. Let me to show what was the results. This is the cooking time prediction for an independent set of samples, updated with 20 samples from the new set. As I mentioned, this is the result that we got, and we consider that was the standard error prediction was small because probably our data also was the histogram was very also not so wide. If this is sometimes makes some effect, and is the reason that the standard error prediction is lower. So this is what we have until now. It led me to present some conclusion of this work. We know that the cooking time, water absorption, and texture of dry beans vary widely by genotypic, and is also influenced by the growing environment, storage condition, physicochemical and microstructural properties, and cooking methods. Another is that the BISNIR and hyperspectral techniques have great potential for predicting the firmness and cooking time of cooked beans simultaneously from a single measurement. And then the robustness of sensible models seems to be affected by the genotypic and phenotypic diversity, planting year, and distribution of the data used for model building. So we propose here to make some periodical update with new data in the way for improving this model robustness and also the generalization. We have worked around 5 years with this in this area, and I think that is open because there are other options, as I mentioned before, that we can use it here to improve the robustness of this model. What I tried my best, my knowledge in food science, as an agricultural engineer also, to try to get this information, and I am pretty sure that we can repeat that and to improve the methods. This is the paper. This is the first page of the paper. Please, if you have any question, even I was also the editor suggests me that was a very good idea to also to share the programs in MATLAB. We have also available the information, the images. We didn't send all this information because it's so heavy, but I think that if somebody is interested on that, I am very happy to follow and also to supporting anything that I can do. Thank you so much for your attention. This is the information that we have, and I am very happy. If you have any question, please, I am open.
Well, thank you, Dr. Mendoza. Now, as we prepare for questions from the audience, you have 2 ways to submit those. One is you can open up the chat box and go ahead and type your question either to myself, to everyone, or to Dr. Mendoza, and we can read those. Or you can unmute yourself and ask the question. In the interim, I'll just thank you again for putting your work in the Plant Phenome Journal, because it's a scholarly publication, and it is something that's supported by the Crop Science Society of America and the American Society of Agronomy to try and engage in sort of this newer work. One of the things I really liked that you highlighted at the very beginning was how multidisciplinary your group was. So I'm going to take the opportunity to ask the first question, and if nobody else has any more, I might ask another one or two. But among your multidisciplinary colleagues, how challenging was it for you guys to all talk the same language and learn to work well with each other? Were there any barriers you had to overcome, and if so, how did you do those?
I think that the very nice thing that was not difficult. I think one thing that I can say that I appreciate that I like to work with many people with different countries, and also because you learn a lot. All people was very gentle to help, and also people from there, in particular, well, the people that is from US, they were very open for to all the persons. So this is one thing that I miss. This is very good, and the communication always was very good because always they have different views of that. So always we have something to discuss and to share and to help. And one thing that I need to say at this point is that this kind of works, the work that I did trying to collect information, is impossible if I am trying to do this alone. Was the people, my colleagues, that collect all this information and I take care of another part of that. Because in another way, could be impossible to get all this information, all this set of information that I present today. Even we have more, but was thank you to them and the good communication that we got. Probably our language are different. Our English probably is not the best, but at least we are able to communicate. I need to say that I appreciate a lot that from because the group helped for that. So great, thank you for your question.
Sometimes I forget I mute myself, so I'm sorry. Any other questions at this point? Go ahead and unmute your microphone with the little red button or type something in the chat there. Oh, here we go. So this question is from Andrew. In addition to applying your method in plant breeding, could the method also be used to label soaking cooking time recommendations on dry bean packaging?
This is a good question. I think, of course, using this kind of technologies, I think that we need also to test more samples because I don't want to try to say we have a lot of future with that in many areas and also for the to know if we can able to put this, for example, in to set up something. But in my opinion, now we need to use more data to make sure that the results can be reproducible and also make more to get more information because I get a good results, but I need in addition to do more than that to be able to make sure if it's possible.
I'm muted again. I keep talking to you while I'm muted. I'm sorry. I missed an earlier question from Katie. She said, thanks for the great presentation. Lots of interesting results. I'm wondering if you have any insights on how this work could eventually help breeders as they make their selections either indoor in greenhouses to be more ambitious out in the field.
Sure. If you want to tell that again, this run for the number of samples that you have for calibration of your models. In fact, what we are trying to do, and I remember that it was one of the purpose for some groups in MSU, was to collect a huge amount of information and to be able to develop some models that are able to predict some particular traits in different cultivars or in another application. But one thing that I want to mention at this point, in particular in this area that I know, and also in the area of food, is that the technology today that I saw, as I mentioned 1 month ago in a big seminar, was that the technology is here. The problem that the people, they don't have is the models. The problem is because we don't have enough data to be able to get robust models. Many people present models, but this model, when you use in another environment, doesn't work, or the prediction is very low. So what my recommendation is One thing that I found on that, and I can say and I can share with you, is that this kind of method, when you are able to have the two-band ratios, works well because help to avoid some noise of the signals and help also to get more reproducible data. So what my recommendation is, if another person wants to continue with that, is to follow with the same methodologies, but probably to improve, no, in another platforms that make easier the analysis. But the truth is, if you want to apply in another areas and to go on to make simple methods, is possible. The technology exists. The problem is the models. This is the most difficult thing to get. This is in my opinion. But I think that this is the right way. One comment more is that here I work for another thing that is in ElectroLux. We are trying to predict quality in foods and to improve the quality of the refrigerators, for example. And the problem is the technology exists, but the problem is they don't have the model. We don't have the models. So we need to create that. This is the most difficult part. But it's open, and I feel that it's possible to get anything that you want.
Okay, we already have two more questions. So yes. You obviously gained a lot of interest on this presentation and your paper. The next question is from Ri. I hope I'm pronouncing that correctly. Ri Setahara. According to slide 27, will it be better to include more years of data than to have number of reps within the same year? So slide 27.
Yeah, say again, please. Yes, I am now in the 27 for the model updating, yes.
So the question is, will it be better to include more years of data than to have more numbers of reps within the same year?
No, yes, absolutely. I think that I was short from samples. So even when I feel that I have a lot of information, I can say that this is possible, and even I recommend to use more. But we need to probably to use more new data, but coming from different places or different cultivars, able to mix. We use a special set of data with some conditions. But to improve that and to get some generalization of these methods, absolutely. I highly recommend to use that and to optimize that. If you use more samples, of course, you are going to have better results for that. That's my expectation.
Okay. This question is from Daniel Morris. The hyperspectral data is in image form, but it looks like you just averaged all the responses across pixels, meaning you dropped most of the spatial information. Would it be possible to use local spatial information?
That's a very good question. Thank you. Really, because, of course, I tried. But the problem is we have a powerful computer, but you don't imagine the amount of data that you have there. I try to extract, for example, information about not only the intensity of each beam in the image, also the information that you can get, for example, textural information. How change this textural information of the image? I mean the pixels variation for each beam. This is very rich information that absolutely we can get a very good information probably to extract more information, more robust models. But the point there is very complex because the size of this image is more than at least 1 giga. So you imagine you need to work with a lot of samples. If from each image you are going to extract information. If for each beam, if you want. I tried that, but I spent around 1 month trying to get a model. My results don't improve too much because, unfortunately, I feel that I didn't have enough data. But if you have a lot of data, you have more data, absolutely. This is a great opportunity. But one thing that I want to say here is the mean values or the average intensity values that I got from each image is coming from all this spatial distribution. That is different than when you use near infrared, you measure only a spot or you make a spot measurement. So this helps a little bit to get a similar results using a shorter wavelength range in comparison with the near infrared spectroscopy. So I think that is, of course, could be very interesting. I would like to to read some paper doing more things to these hyperspectral images to extract more information. This is open. Very good question. Thank you.
I have one more question, but if anybody else has a question, go ahead and unmute your microphone. Seeing none. I mentioned at the beginning when I introduced you, Dr. Mendoza, the thing I found most innovative from what I do with near-infrared spectroscopy is your use of the two-band ratios.
Yes.
And I haven't gone back to look through your response to the reviewers and all that, but can you inform us if you've seen other people do that, or what led you to do that, and how useful that was?
Yeah, it's interesting, because this is the first time that somebody asked me about that when I received your comments about it. Yes. I tried many common methods that we use. For example, these use first derivative, second derivative, people recommend that. But sometimes the problem when you are trying to measure in when you are not going to prepare your sample, you are not going to have some homogeneous sample, you are using the wrong material. The main problem that we have, for example, there is that the size of the samples are not the same. It is affected in particular when you are talking about the reflection of the samples. So one thing that I did that I know is that using this kind of two-band ratios, because I get a lot of information, and at the end I use 100, the base 100. I feel that all this noise that I got from the different size of the samples improve a lot. In particular, when, for example, it's very difficult in hyperspectral imaging to have a homogeneous distribution of the light. When you use this kind of method, all the images start to be more homogeneous because you are using the ratio. So this, in my opinion, was the secret, because it improved a lot the results. And in any test that I make later using these two-band ratios, using even first derivative, second derivative, or continuous Welle transform, improve the results. So this is one thing that, for example, I would like to recommend to the people to continue with that.
Well, and I didn't hear you just mention it, but one of the things we see in regular near-infrared spectroscopy is that there's certain spectral regions that are have absorbance of multiple different chemical bonds, right? And
yes.
So my thought on your using two-band ratios was you were getting away from some of those things that might show absorbance at multiple bands, if that makes sense.
Yes. Thank you for your question. I want to explain something that always was my concern, and many people ask me. If I repeat this kind of samples, for example, for different sets, one thing that I agree with you, probably I am going to lose this correlation with the wavelength that I am looking. But more than to look here, information from, for example, from one specific component, that sometimes, for example, you know what is the range that you can find water, you can find a specific chemical. But here we are talking the relation that you have with the microstructure of the product, to know what is the texture and also what is the cooking time. So we are not measuring here a property that is, you know exactly what is the wavelength that you need. When I repeat different tests, different samples I make my models, I know that my wavelengths were not always the same. It was not possible because what changed? Probably the microstructure of the product. So the absorption of the light and the reflection are going to be different. What I propose is that we need to use and to get more and more data, that we are going to combine this data to get information that at the end we are able to get probably around the same wavelength range. Let me to talk about wavelength range more than to talk about this is the wavelength 950 or I don't know, to get a specific number, because it's so difficult. This is my view, but I agree with you. This is one thing. I cannot recommend exactly what is the best wavelength to measure, for example, texture or probably a cooking time. But I want to say that in the future, if we have more information, I am pretty sure that these models are going to be robust because we are not measuring chemical properties. We are measuring here sensorial properties. That is more difficult. That is related with the microstructure of the product. So that's my view.
Okay. Well, one last call for any more questions. We have been an hour so far, so maybe take one more question if anybody wants to jump in.
Yes.
And if not, thank you, Dr. Mendoza, for an excellent seminar, excellent responses to questions, and we'll look forward to your future work.
Thank you so much for this great opportunity. I really appreciate and I expect to continue contributing with my